Greetings everyone, my name is Dr. Matthew Clark and I am a postdoctoral fellow at MIT and incoming professor at the University of Illinois Urbana-Champaign. My paper is entitled An Open Source Framework for Modeling Aircraft Noise in Urban Environments. So to start off with, basically there are currently a few tools out there developed federally to study aircraft or to get a better assessment of aircraft. One being the FAA's ADET tool and the second being NASA's Air Noise UAM tool. However, there are some limitations of these tools and I've listed some here. The lack of specific data, NPD data, which is noise powered distance data. The second being that these tools are not really equipped to do interdisciplinary analyses to understand not only the noise, but also the performance of the aircraft during flight. And lastly, there's a lot of difficulty in acquiring these packages due to cost as well as citizenship restrictions. So as a result of these shortcomings, we wanted to create a tool out there that can essentially allow for the prediction of aircraft in urban cities and do so in a way that's accessible to the community. So, like I said, this urban air mobility noise assessment framework is divided into three areas, or broken down into three stages. The first being digital elevation pre-processing, the second being mission simulation, and the third being noise post-processing. So, looking at this, first off, let's examine the pre-processing stage, which really involves first downloading a digital elevation map on a particular region of the Earth. Then we essentially construct a rectangular array of microphones on a particular region. We define our flight trajectory, and then obviously, as you can imagine, the noise that an aircraft produces is not going to be heard far away from the aircraft. So what we want to do is to create stencils, or essentially subsets of microphones where the noise is calculated at. The second stage of the framework involves mission simulation, and this can be broken down further into three areas. Number one is vehicle definition. So here we're going to use three UAM aircraft, the first being a stop rotor, the second being a tilt rotor, and the third being a multi-rotor aircraft, which is wingless. And as you can see here, we have the weight breakdown for each aircraft. The second is the flight profile definition. So we wanted to make sure that we have a good understanding or a good reflection of the flight profiles, or realistic flight profiles. So attention was placed on modeling specific segments corresponding in accordance to federal regulations set in the Part 14, Part 35, or Part 23, as you can see here. And we've done so for all the aircraft of this in this study. Lastly is the mission solving process. And for this process, we're going to use a cadre of tools, all built within the fork of SWAV, which was essentially the bedrock for these simulations. So for the aerodynamics, we use the vortex-Lassen method to compute the forces. For the battery model, as well as the rotor model, we use from previous work. So we essentially coupled a blade element vortex theory model with a simple a simple battery model, and then we use a brush DC model for the motor. Lastly, to capture the noise, we use a frequency domain-based approach. So we use Hansen's model for noise, and we couple it with Brooks, Pope, and Marcolini method to capture the broadband component. However, it must be noted here that the blade vortex interaction and blade wing interaction noise is not included. The final stage of this process is the post-processing. First, we convert the calculated sound pressure levels to the A rating scale using the equation shown here, and then we essentially use two metrics in this study. First is the maximum A rated noise level, and then is the equivalent A rated sound level as defined in these slides. So, the fun part. The first study we conducted was the flyover noise study, and for this study we essentially compared regular flights over a highway to a highway noise model. And for the highway noise model, we used the Federal Highway Administration model, as you see here. This model can account for several factors, including the number of cars, types of cars, the frequency of cars, the speed of cars, as well as other environmental factors in this study. The general trend we see for this first study is that as the aircraft gains altitude, the noise level decreases. For the stop rotor and tilt rotor, we see here that all of the altitudes result in noise levels below the highway noise level. However, this cannot be said for the hexacopter aircraft, which pretty much essentially dominates the noise spectrum. Only in certain areas close to the highway, at certain altitudes, at certain high altitudes, does the highway noise actually is higher than the aircraft noise. The second study shown here is the approach or the arrival and departure study of aircraft to a particular vertiport. And the reason for this study is that we want to understand if there are essentially best practices for UAM operators. What we did is that we essentially modeled the aircraft to arrive at the same angle. However, the departure or the departure leg was modeled at different angles, ranging from 0, 45, 90, 135, and lastly 180 degrees. What we gathered from this study was that there was not necessarily one ideal angle for the stop rotor or tilt rotor aircraft. However, depending on the range of noise you're trying to mask, they are different angles. However, you see here that the stop rotor aircraft, the best angle for both ranges of noise seems to be the 180 degree takeoff phase. So therefore, modelers should look to create a single bidirectional route for this particular aircraft. The last study conducted was an urban environment fleet noise study. And in this study, essentially, we first gather the major airports within the Los Angeles area. As you can see here, 9 vertiports, which comprise of 8 existing vertiports and a vertiport located at the Disneyland Park. And the ranges as well as the routes are shown below. The preliminary results show that in terms of maximum noise level, the hexacopter aircraft completely dominates the other 2 aircraft. The stop rotor aircraft does produce a larger footprint, and in fact, if you look carefully at the top left plot, an observer directly below the flight platform would indeed hear the vehicle. However, this is marginal compared to the hexacopter aircraft. Secondly, on the lower row of plots, we have the equivalent aviated sound pressure level over a period of an entire day. And as we can see, the noise levels from both the stop rotor as well as the tilt rotor aircraft are pretty much masked within the airport noise. However, the levels for the hexacopter aircraft are not, and this suggests that this aircraft will indeed have a significant impact on commuter on the neighborhoods below. To put this in perspective, we want to have an idea of what's the volume or what's the percent increase in these equivalent A rating in this equivalent A rating scale. So what we did here is we compared flights for 60-minute intervals, 30-minute intervals, as well as 10-minute intervals throughout the day for each aircraft, and we can see here that the hexacopter aircraft sees increases of about 250% in some areas of noise level, of particular bands within the noise spectrum. In addition to that, we can gather from the lower row of plots that there is actually a net negative effect of operating these aircraft, as we can see that from particular points shown on the plot. The energy consumption of these aircraft is shown on this slide. What we conclude basically is that the hexacopter aircraft consumes about 4 times as much energy as the other aircraft. And we also see that from both a noise and an energy standpoint, the tilt rotor aircraft is the most efficient. There's still a lot of work to be done in this model. First, we want to improve the broadband as well as the BVI and BWI components. We also want to do some validation of the study and then accelerate the noise simulation using JATS. And lastly, one of the things we want to do is to expand this study to include areas such as San Francisco, Dallas-Fort Worth, and New York. Thank you very much.